fields. Today we will move on to the next chapter, that is lithosphere. In this chapter, children, we will be studying about the meaning and importance of lithosphere, the Earth's interior and composition, rocks, forces of the earth crust, glaciers, underground water, and sea waves. So let us know or study about lithosphere. As we all know, in the spheres of Earth, we have atmosphere where you can see we are having, this is biosphere, we are having atmosphere, that is air, we are having lithosphere, that is earth, and hydrosphere, that is water. So these are all particular chapters what we are going to study. In the last class, we had studied about the earth. Now we will study about the lithosphere, atmosphere, lithosphere, biosphere, and hydrosphere. Lithosphere. When we tell lithosphere, what do we mean by the word lithosphere? Lithosphere, children, it is derived from the Greek word lithos, meaning rocky or stone. It is primarily the rock and stony stony part covering the whole Earth's surface, on which the interaction of other geospheres happen. The term was coined by Joseph Barrel in 1914, who first studied the motion of lithosphere, a molten layer, that is asthenosphere. We will be studying in this. See, you can see here, this is the atmosphere where we are having this one. This is the lithosphere on the top, which is found on the upper most solid part. This we call it as a lithosphere. This is inside the earth as we go down, as we studied in the first chapter. So what is lithosphere? The lithosphere, children, is the rocky outer part of the earth. It is made up of the brittle crust and the top part of the upper mantle. The lithosphere is the coolest and most rigid part of the earth. The lithosphere includes the brittle upper portion of the mantle and the crust, the outermost layer of Earth's structure. It is bounded by the atmosphere above the asthenosphere, which is the another part of which is another part of the upper mantle. You can see it. This is mantle. This is the lithosphere. The rocks of the lithosphere are still considered elastic. They are not viscous. The asthenosphere is viscous, and the lithosphere, asthenosphere boundary, we call it as lab. So is the point where geologists and the rheologists, scientists who study the flow of matter, mark the differences in the ductility between the two layers of the upper mantle. So all the rocks of the earth, from the mountains to the sea floor, is included in the lithosphere. So this is the earth's lithosphere, what we are having, children. What we are having. The lithosphere consists of rocks, minerals, soils, etc. On this, the life exists in this layer with the help of the atmosphere and the hydrosphere. The continents, you can see these are the continents, are the parts of lithosphere where different landforms like mountains, plateaus, plains are found. Now we will move on to the interior part of Earth's interior and its composition. Our planet Earth is as old as 4.6 billion years old, and still there are changing process of changing. Man is in quest of understanding this change, who is eager to know what is there inside the earth. Still, it is mystery to the man. With years of study and research, human beings have been able to get more information about the materials which is inside the earth up to 10 to 12 kilometers only. Going beyond, if we go beyond the depth, children, here it is very difficult because the temperature increases. For every 32 meters, 1 degrees Celsius of temperature increases. So it is difficult to go. So to understand more about the earth crust, the earth's interior, humans are dependent on indirect evidences such as the seismic waves, volcanic materials. The Earth's interior, it comprises of various materials in different forms. On the basis of the density of material, chemical composition and physical state of matter, the Earth's interior is classified into 3 layers. One is you are having the crust, which is the outer part. Then you are having the mantle, and then you are having a core. So these are the 3 parts. Now let us study about the crust, children. See here, this is the crust here, children. It is a layer of sand and rock varying from 5 to 50 kilometers thick. This crust is the uppermost layer of the earth. It is rich in silica, aluminum and magnesium, children. The depth of this layer is around 60 kilometers of the surface of the earth. In the upper part of the crust, only lighter materials are found. We call that as seal. That is we tell SiAl. So this seal means silica and aluminum. Si stand for silica, Al stand for aluminum, or we call it as a continental crust. The lower part of the crust is rich in silica, it is rich in silica and magnesia, and it is called as Sima, S-I-M-A. It is called as a Sima, or we call it as an oceanic crust. So we can see here, children, what I told, the crust, the mantle, where you can see here, and here we are having the oceanic crust. Cl, the continental crust. Here we are having the Sima. Here we are having the US mantle in the upper mantle, where you can see this is the lithosphere. This is the continental crust. This is the upper mantle. And in geology, the term SiAlCl refers to the composition of the upper layer of the Earth's crust, namely the rocks rich in aluminum silicate minerals. It is sometimes equated with the continental crust because it is absent in the wide oceanic basin. But Cl is a geochemical term rather than a plate tectonic term. As these elements are less dense than the majority of the earth elements, they tend to be concentrated in the upper layer of the crust. The uppermost layer of the crust, we call it as Cl, consisting of silicate and aluminum. Si stands for silicate and Al stands for aluminum. And on average, the thickness of the Cl is still 25 kilometers from the surface. The continents are composed mainly of lighter rock materials formed from silicon and aluminum. So the Cl is thick over the continents and very thin or absent on the ocean floor, especially the Pacific Ocean. The average density of the Cl is 2.7 grams per cc. The name Cl has been taken from first 2 letters of silica and of aluminum. It is often concentrated to simmer the next lower layer of the earth, which is often exposed in the exposed in the oceanic basin, and the nickel iron alloy core, sometimes referred as NIF. These geochemical divisions of Earth interiors were first proposed by Eduard Suess in the 19th century. This model of the outer layers of the Earth has been confirmed by the petrographic, gravimetric, and seismic evidence, children. Now, when we move on to the oceanic crust. So, what do we mean by oceanic crust? Oceanic crust, extending from 5 to 10 kilometers beneath the ocean floor, is mostly composed of different types of basalts. Geologists often refer to the rocks of the oceanic crust as sima. So, the oceanic crust is dense almost 3 grams per cubic centimeters, and oceanic crust is constantly formed at the mid-ocean ridges where tectonic plates are tearing apart from each other. As magma that wells up these rifts in Earth's surface cools, it becomes young oceanic crust. The age and density of oceanic crust increases with the distance of the mid-ocean ridges, children. Now we will be moving on to the next, that is the oceanic crust, where this one, children. Here we are having, you can see here, this is the lithosphere, this is the asthenosphere, this is the mesosphere, this is the outer layer, and this is the inner layer. Now we will move on to the next topic, that is the mantle. So the mantle, this is the mantle, that brown color, children. So the mantle, children, is the second and the middle layer. It is the second and the middle layer of the earth. The depth of this layer is 2,900 kilometers. From the surface, the metals are in semi-liquid or partially molten state, which is called as a magma. We call that as a magma, and the mantle is composed of dense and rigid rocks which have the predominance of minerals like magnesium and iron. The mantle has two parts. One is the upper mantle and the second one is the lower mantle. The upper mantle, or we call that as the asthenosphere, is partially in molten condition, and lower mantle or the mesosphere is in solid condition. The contact zone of the crust and the mantle, we call that as the Mohorovic discontinuity, or we call it as moho. The boundary that separates the mantle from core, the boundary, this black color, which separates mantle from core, we call that as a Gutenberg disunity. We call that as a Gutenberg disunity. Hence, the rocks are different in chemical composition from those of the above. So, now let us know about the mantle. As I told, it is a solid bulk of Earth's interior. It lies between the Earth's dense superheated core and its thin outer layer, the crust. It is about 2,900 kilometers thick and makes up a whopping of 80% of Earth's total volume. The mantle is the most solid bulk of Earth's interior. whooping, as I told, total volume. As the earth began to take shape about 4.5 billion years ago, iron and nickel quickly separated from the rocks and minerals to form the core of the new planet. The molten material that surrounded the core was the early mantle. Over millions of years, the mantle cooled, water trapped inside the minerals erupted with lava, a processing called as outgassing. As more water was outgassed, the mantle solidified. So this is about the upper mantle what we are having, children. Asthenosphere, it is called 2372 degrees Fahrenheit, and the flows at the rate of growing nails, part melted. It is made up of hot rocks. It is more dense than the oceanic crust and higher pressure, 250 kilometers thick, thinner than the lower mantle. So I told you about the upper mantle. So when we move on to the upper mantle, children, it begins just beneath the crust and ends up at the lower mantle. The thickness is 200 to 250 miles. The entire mantle is about 1800 miles thick, which means the lower mantle makes up a bulk of this part of the earth. So the temperature of the mantle near the crust, it ranges from 900 to 1600 degrees Fahrenheit. It's get hotter at a greater depth, and the lower mantle near the core is as hot as 7 degrees Fahrenheit. The upper mantle is not uniform throughout. The topmost thin layer of it is very similar to the Earth's crust. Together with the crust, we call it as the lithosphere. Below the lithosphere is a layer of upper mantle called as the asthenosphere. We are having the convection in the mantle. This is made up of the rock that is fluid and can move. It is this fluidity that powers the movement of the tectonic plates of the Earth's crust. Circular convection cycles in the hot, fluid upper mantle. Rock move the plates over the surface of the Earth. Now we will move on to the lower mantle. The rest of the mantle between the upper mantle and the outer core, we call that as the lower mantle. You can see here. This one. So it is denser and hotter than the upper mantle. The lower mantle is more solid than the upper mantle. So what is there? Which type of minerals do we find here? We find olivine, magnesium and iron. So this is ranges from 400 miles on the surface to 2800 miles below the surface. It is incredibly large and takes most of the volume of the earth. It is deep inside the earth. The temperature and the pressure of the lower mantle are extremely high. And the pressure in the lower mantle is a maximum of 1.3 million times to that of the surface, creating minerals we normally would not see in the crust. This is what I call the Mohoric disunity, isn't it? The Mohoric disunity. See, this is called as the Conorod disunity between the upper crust and the lower crust. Between the upper crust and the lower crust. This we call it as the Mohoric disunity between the upper mantle and the lower mantle. And this we call it as repetitive disunity between the upper mantle and the lower mantle. This line what we call, this we call it as Gutenberg continuity between the lower mantle and the upper mantle. So between the lower mantle and the outer core, children. This line what we call, this is the inner core. This is the Lehman discontinuity between the outer core and the inner core. Now we will move on to the core. Now we will move on to the course. Core. The core. This is the innermost part of the earth, children. Innermost part. This core. So the depth of the layer is up to 6,371 kilometers from the surface. The most important metal of this core is nickel and ferrous. It is nickel and ferrous what we find. What we find, and nickel and ferrous what we find here, and also it is known as NIF, N-I-F-E, NIF. It is also called as the NIF. So the core is between the two sub layers, that is the outer core is known as the molten core, the outer core here. This is also known as a molten core, and the inner core is known as the solid core. So the outer core is about 2200 kilometers thick and is mostly composed of a liquid iron and nickel. So for it is NiFe, what we call alloy of the outer core is very hot, between 4,500 degrees and 5,500 degrees Celsius Fahrenheit. The liquid metal of the outer core has very low viscosity, meaning it is easily deformed and malleable. It is the site of violent convection. The churning metal of the outer core creates the sustains Earth's magnetic field. The hottest part of the core is actually the Bullen discontinuity, where the temperature reaches 6,000 degrees Celsius, as hot as the surface of the sun. This is about the inner core. So the inner core is a hot, dense ball. See, this is the inner core. You can see here. This inner core is a dense, hot, dense ball of iron. It has a radius about 1,220 kilometers. Temperature is in the inner core is about 5,200 degrees Celsius. The pressure is nearly 3.6 million atmosphere. The temperature of the inner core is far above the melting point of the iron. So the pressure and the density are simply too great for the iron atoms to move into a liquid state. Because of this unusual set of circumstances, some geophysicists prefer to interpret the inner core not to be a solid but as a plasma behaving as a solid. So we are also having some of the deepest land mines in the world. We are having the Kola Superabro, which is the deepest hole in the earth. We are having the Kimberley diamond mine, the big hole in South Africa. We are having also the Kolar gold mines, that is the KGF. So in the next class, children, I will stop here. In the next class, we will be moving about the next topic, that is rocks. Thank you, children.